Good day everyone, this is Oscillation and Wave Motion, and I am Jasmine Richard Signy, your presenter for this chapter. So, learning outcomes, define vibration, describe and apply simple harmonic motion, relate energy and speed in such systems, classify types of wave phenomena, describe the motion of a simple pendulum, and solve for simple problems for simple harmonic motion. So, our topic outline. Types of wave, properties of wave, concept of sounds, and simple harmony. So this is a wave. A wave can be described as a disturbance that travels through a medium from one location to another location without transporting matter. So this is a transfer of energy without transporting any particles in the medium. Particles vibrate in fixed motion. So more information about wave motion. So wave is a motion of disturbance, and the difference between wave and vibration is the fact that vibration does not carry an energy with it. A medium is a physical environment through which a disturbance can travel. For example, water is the medium for ripple waves in a pond. So next, waves that require a medium through which to travel are called mechanical waves. An example of mechanical waves are water waves and sound waves. And last, electromagnetic waves that are visible, such as light, does not need any medium. So wave types. A wave that consists a single traveling pulse is called pulse wave. Whenever the source of a wave motion is a periodic motion, such as the motion of your hand moving up and down repeatedly, a periodic wave is produced. A wave whose source vibrates with simple harmonic motion are called sine wave. Thus, a sine wave is a special case of periodic wave in which the periodic motion is simple harmonic. So here are the two types of longitudinal waves that gonna be critical for this lesson. So first is the longitudinal wave. Imagine that this is a spring attached on the wall here, and you are moving the spring from left to right. And some of the basic parts are gonna be compressed. Over here you can see that they are compressed, and some of it are away to each other. But of course the oscillation is there, so you will get this movement of compression and separation. The movement of the particle in its fixed position is going to be the same direction, so they're gonna be just like from like this, from that. But on the second type of wave, which is the transverse wave, it moves up and down, and it forms trough and crest. So here they move up, they move down, up, down, up. The position of a fixed particles are going to be 90 degrees in the movement of the particles, and that 90-degree angle that suggests this wave is a transverse wave. So let's have a closer look of this longitudinal wave. So they vibrate in parallel, so they're just going up, down, from right to left, right to left. So here we have the compression, and here we have they are apart to each other. It's called refraction, and here is the rest position of the wave. And here now in the transverse wave, we have different parts of it. So first is the crest, which is the top of the side of this. From going down up, that is crest, and when you go down, that is the trough. And this line is the rest position. And from the left to the right is the time or distance. Then amplitude is from the rest position up to the crest, or it can be from rest position up to the trough. And from crest to crest, it is the wavelength, or trough to trough, it is the wavelength. And one crest to and one trough is one cycle. So here are the terms that are important. So wavelength, this is the distance between adjacent particles that are the same point in their vibration. So in transverse, it is the distance between two adjacent crests or trough. And in longitudinal wave, it is the distance between two adjacent compression or refraction. Amplitude. This is the maximum displacement of particle from the rest position. In transverse, it is the distance between the rest position and the crest. Velocity. This is the distance traveled per second, and this is measured in hertz. Wavefronts. This is the location of all particles of the medium in the same vibration state. It is perpendicular to the wave direction. The distance between wavefront to the next is wavelength. So here are the live application of oscillation in wave. So what you can see now is a horn and the guy who is demonstrating it. So he's going to use the sound wave. Sound wave is a longitudinal wave. So now he's gonna blow the trumpet to get some size and play the note. So as you can see, the bubble wasn't disrupted or anything. So it means that sound wave does not, it just passes through, but it doesn't disrupt anything. It, so sound wave is a type of wave that doesn't make anything. It's just going right through it without disturbing anything. So here is another example of oscillation. So it's a called catchy wave. A wave occurs when the fabric is bounced from its equilibrium position and the energy is transferred down to the fabric. When the wave reaches the end of the fabric, it bounces back similar to the when sound wave hits a barrier and creates an effect. So if you pull the fabric tighter, the wave travel faster. This is because the higher tension in the fabric. The higher the restoring force, and the faster the fabric reacts to send the wave on its way. So when it comes to wave, there are properties that we need to be aware of, and these are just four properties: deflection, refraction, diffraction, and interference. So first is reflection. Reflection is a property of wave that bounces back when it hits a surface that it cannot pass through. So first, when a wave hits a surface which is cannot pass through, it bounces back. So here we have a let's say a mirror, and then here's a flashlight, and the light is a wave. It's a kind of wave, and it hit the mirror and it bounces back because it cannot pass through the mirror. So here, this is the incident ray, while this is the reflected ray, and this is the angle of incidence. We're in the middle of the two incidents, and this is called the angle of reflection. So if in real life, this is what you're gonna see. There is a light, and then the light had been reflected to the other side because it cannot pass through here. Only could go here. So more example is this ball, and it cannot pass through, so it bounces. And same with the scenario wherein the reflection on copy D this reflects this scenery because it cannot bounces back. So refraction, so this is the bending of wave due to a change of speed as it passes through one medium to another medium with different density. So when a wave is moving from one medium to another, it changes as it enters the second medium, which causes the phenomenon, and this is called refraction. So this line is the boundary. And we have one substance and two substance. One is gas and one is liquid. So this is the incident ray, and the angle created by the incident ray is called the angle of incidence, while this is the refracted ray, and the angle created by refracted ray is the angle of refraction. So in this picture, there is two medium, which the first medium is gas, and the second one is the liquid. That is why light wave bended and caused the straw to appear distorted, but it's not really broken, it's just its apparent appearance. Another one is when someone is trying to fish using a spear. In the image, you will see the real fish is actually nearer than the image due to the bending of light. And lastly is when an image appears bigger or smaller through a glass. So the third property that we will discuss is diffraction. Diffraction is almost the same as refraction because it also has a bending of waves. So here you can see it's some type of wave, and once there's a wall that had been disrupting it, cut it to half, then it starts to bend from here and return to its original state like this. So here are the examples of this fraction. So first, this fraction of wave is a wave that emerges in narrow slit. So if there's a wave that is parallel, once it go to the slit, it will go like this. So what does this tell us? This tells us that the narrower the edge, corner or hole, the bigger the bend it once it comes through. So next is here. It's the same as the first one, but there are two holes. So this one is a wave interference wherein there are two waves that overlap or interferes each other. So they are both interrupting each other or interferes because it overlaps waves. So next is this one, wherein it has a bigger hole than this one. So as you can see, it's not that big of a wave when it passes through the hole. So last is when the barrier is longer than the wavelength. The wave doesn't bend that much. So as you can see here, here's the parallel waves, and then here's the wall, but it doesn't break. It didn't bend that much. So here's a real life example. So here we have a flashlight, and from here it has a small hole. So when the wave comes out, the wave light is bigger. It came out big. While here we have some sort of like a megaphone. So when the wave comes out, because it has a bigger hole, the wave comes out not much that big than the other one, than this one. So here we have also the light, wherein there's a small slit from the door, so it comes out a big wave. So last is the interference, wherein the effect of the interaction between two waves when they meet. There are two types of interference. One is constructive and second is destructive. So if two waves meet and they create a bigger wave, then this is called a constructive interference. So in this case, the two waves are in a phase. That's why the energy of the wave combined, resulting the amplitude of the wave being twice as higher as the amplitude of their original wave. Wave X plus wave Y produces a resultant, wave Z, which has a higher amplitude. So, if two waves meet and they were able to lose all the wave, then it is called destructive interference. So, if two waves are out of phase, the amplitude of the first wave cancel out the amplitude of the second wave and produce wave with zero amplitude. So let's watch this. So as you can see, they hit on a different side. So this is destructive interference wherein wave 1 plus wave 2 is equal to no wave. And they went back to the original. Then constructive interference is when they made a bigger wave, which in they hit on the same place. So an example of destructive interference are noise-canceling headphones work by using a microphone to pick up the frequency of incoming waves. Then the headphone sends out a wave that is the exact opposite, so canceling out the sounds. That's why we hear music in noise-canceling headphones. Another example is two people singing the same song and they were singing together, making the song louder than they are just singing it alone. So next is the concept of sound. Production of sound. So every sound begins with a vibrating object, such as vibrating from of a tuning fork. So a compression is the region of a longitudinal wave in which the density and pressure are at the maximum. So sound wave is considered as a longitudinal wave, and longitudinal wave travel in the form of compression and refraction. A refraction is the region of the longitudinal wave in which the density and pressure are at the minimum. So sound waves are longitudinal, and the simplest longitudinal wave produced is by vibrating object and can be represented by a sine curve. So here is a representation of a longitude of a sine curve. So frequency of sound. Frequency is defined as the number of cycles per unit of time. Sound wave that the average human ear can hear have a frequency between 20 to 20,000 Hz. So this is called the audible sounds. Sound waves with frequency less than 20 Hz are called infrasonic, and sound waves with frequency about 20,000 Hz are ultrasonic waves. So infrasonic, usually we know that whales can hear such wave that we cannot hear, and from 20 Hz to 20,000 Hz, that is edible to person, to people, and more than 20k Hz is audible to the other species such as bat, which is called ultrasonic. So frequency and pitch. Wave of an audible sound wave determines how high or low we perceive the sounds to be, which is we call pitch. Now the frequency of a sound wave increases, and so the pitch will also rises. The frequency of a wave is the objective quantity that can be measured, while the pitch refers to how different frequencies are perceived by the human ear. So now let's talk about high frequency sound waves. Simply, high pitch sound has high frequency and low pitch sound have a low frequency of sound waves. The speed of sound. So the speed of sound depends on the medium. The speed of sound also depends on the temperature of the medium. So remember that that the speed of sounds depends on the medium, and one of the main properties of the medium is the density of the medium, because wave consists of particle vibration. The speed of wave depends on how quickly one particle can transfer its motion to another particle. For example, sound waves generally travel faster through solids than through gas, because the molecules of a solid are closer together than those of a than gas, and thereby reducing the chance of having one particle transfer its motion to the next particle. So the speed of sound also depend on the temperature of the medium. So this is most noticeable with gases because of as the temperature increases, there is a higher random motion, the more the chances of collision, and the higher the chances of sounds traveling faster. So this is the speed of sound. So again, as you can see that the density of the gas is much less value of the time because much more higher because the larger molecule will take a large amount of time for them to travel, and lighter molecule the faster they travel. So liquid have a higher molecule than gases, so as well as solids. So the solid is higher than the liquid and the gases. So now let's talk about the propagation of sound waves. So sound wave propagates in three dimensions. Remember that the sound have three-dimensional motion with respect to sound waves. So we can think of a sphere sound wave as a spherical wave, generally graphically in terms of two dimensions. So the circle here represents the center of compression and we call wave front. So this is the center of compression, and as you go onward, you notice the peak here represents the compression and the drop in the middle of the refraction. So you have a series of a compression and refraction going in the form of spherical waves that travels from radially outward from the center where the source lies. So radial lines that are perpendicular to the wavefronts are generally called rays, and the sine curve is used in our representation to represent one single ray. Now, when the source is at a large distance with respect to the wavelength, we can approximate spherical wavefront with parallel lines. Uh, So think of it as a spherical wavefront, nearly parallel. So that's why we can say that these waves are called plane waves, and it is treated as one-dimensional wave all traveling in the same direction. So Doppler effect. The Doppler effect is an observed change in frequency when there is a relative motion between the source of waves and an observer. So because frequency determines pitch, the Doppler effect affects the pitch heard by each listener. Although Doppler effect is most commonly experienced with sound wave, it is phenomenon common to all waves, including electromagnetic waves such as visible light. And because of the relative motion, there is a changes in frequency, and we call it the apparent frequency. And it's generally given as frequency apparent equals to V plus minus V naught over V plus minus Vs or times the actual frequency. So this V represents the velocity of sounds, and this V naught is the velocity of the observer, and Vs is equal to the velocity of the source. So let's say that the source and the observer are moving in the same direction. So they are so this observer is moving from left to right, and this source is also moving from left to right. So the velocity of V naught and this is going with the velocity of S. Notice that the sounds that is received by the observer in this direction, and we need to take consideration the relative velocities between V and V naught because they are both traveling in their same direction. So we will consider them to be added. So it becomes V plus V over V plus V source. So let's go to another example. Let's say that the observer's velocity is 0, and the source is going to be to the direction of the observer. So that would be uh, frequency apparent V is equal to apparent is equal to V over V minus V naught, because the keyword is if different direction we add and if same direction we subtract. So sound intensity. As sound waves travel, energy is transferred from one molecule to next. The rate at which this energy is transferred through a unit area of the plane wave is called the intensity of the wave. Because of the power is defined as the rate of energy transfer, intensity can also be described in terms of power. So because of power, power is defined as the rate of energy transfer intensity and can also be described as the terms of power. So intensity is power by area. So intensity is the rate of energy transfer over a given area. So the main reason we use 4 phi r square is because the sound waves are spherical and the surface area of a sphere is 4 phi. So the r here represents the distance from the source. Now the intensity has a unit watts per meter squared. And the intensity equation shows that the intensity decreases as the distance r increases. So this occurs because the same amount of energy is spread over a large area. So sound intensity. Human hearing depends on both the frequency and the intensity of sound wave. Sounds in the middle of the spectrum of frequency can be heard more easily than those at the lower and higher frequency. So this is the speech region, which is the most audible form of the region. So this has a 1 times 10 to the power of negative 6 watts per meter squared, while threshold of pain is around 1 times 10 watts per meter squared, while the threshold of hearing is the minimum amount of energy or the minimum required for the sound, that is 1 times 10 to the power of negative 12. The intensity of a wave approximately determines its perceived loudness. Relative intensity is the ratio of the intensity of a given sound wave of the intensity at the threshold of hearing. Because of the logarithmic independence of perceived loudness or intensity, using a number equal to 10 times the logarithm of the relative intensity provides a good indicator for human perception of loudness. This is referred to as a decibel level. A dimensionless unit called the decibel is used for values on this scale. However, loudness is not directly proportional to intensity. The reason is that the sensation of loudness is approximately logarithmic in the human ear. So this is the conversion of intensity to decibel level. So decibel level is 10 logarithmic of I over I0, which is I is the intensity of the wave, while I naught is the intensity at threshold of hearing. So next is force vibration and resonance. So let's take an example. Let's say we have a pendulum attached with a spring and say two of them are vibrating. These two pendulum is gonna force the other two pendulums to vibrate in the same frequency as these two pendulums. Now, the vibration of the pendulum that has the same frequency or the same mass will start to vibrate more rapidly and increase its wavelength for each interval. This is what we call a forced vibration. If one of the pendulum is set in motion, its vibration can be transferred by the rubber band and to the another pendulum. So now resonance phenomena, where the frequency of a force is being applied to a system matches the natural frequency of vibrating system. This causes a larger amplitude of vibration. For example, if you vibrate one of the blue pendulum, that will cause the other pendulum to have the same frequency and vibrate, and cause the second pendulum to have much longer and much higher amplitude of the vibration. This is this here is the common sense of resonance. So if one blue pendulum set motion, only the other blue pendulum will move whose length is the same and will eventually resonate. So here we have the human ear. So the human ear is divided into three sections: outer, middle, and inner. So sound waves travel through the three region of the ear and then transmitted into the brain as impulses through nerve ending to the basilar membrane. So first, it's going to the outer inside this, and in this thin layer is the eardrum, and it will start to vibrate when a sound wave came, and it will vibrate the anvil and going to the hammer until it went to the basilar membrane. And after the basilar membrane, it will now going to be transferred directly to the brain, which result to the final auditory nerve. So, standing waves on a vibrating string. So, vibration on the string of a musical instrument usually consists of many standing waves, each of which has different wavelength and frequency. The greatest possible wavelength on a string of length is lambda. L is lambda. So, 2 lambda equals to L, and the fundamental frequency which corresponds to the wavelength is the lowest frequency of the vibration. So we know that the frequency is velocity by wavelength. So we can write it as wavelength is 2 lambda. So F1 can be written as V by 2 lambda. This is EF1 here is called as the fundamental frequency. So the term fundamental frequency basically states that this is the minimum frequency that is first starting frequency for any of these vibrations. So there are multiple sets of harmonic series that can form. So we already discussed that when you start one vibration, you will have one cycle that can end 2, 3, or 4 cycle and so on. And their amplitude is this one, which is lambda 1 is equal to 2L, lambda 2 is L, and lambda 3 is 2 over 3L, while lambda 4 is equal to 1 half L. So the equation would be here, would be V naught is equal to 2L, while this one is V over L, this is 3V over L, 2L, sorry, while this is 2V over 2L. So next, let's talk about the standing waves in the air column. In an air column, so if both ends of the pipe are open, so there is this case all harmonics are generally present, and the earlier equation for harmonic series of vibrating string can be used the same way. So we can use the same frequency for a pipe that is open on both ends, which is frequency is equal to harmonic number times speed of the wave on the string all over 2 times the length of the vibrating string. So now what if you have a one end of the pipe is closed and there is a node at the end with the antinode at the one end and a node at the other end, a different set of standing wave occurs. In this case, only odd harmonics are present, which is frequency is equal to harmonic number times speed of the wave string times 2 all over 2 times the length of the vibrating string. Now, each of the harmonic is an integral multiple of the fundamental frequency. So, the harmonic series is a series of frequency that includes the fundamental frequency and the integral multiple of the fundamental frequency. So, for example, if you want to find Fn, the nth frequency, so it becomes n times b by 2s. So, where n can be 1, 2, 3, and so on. So frequency can represent the harmonic number, which is n, which is the type of number of frequency that you want, over times the speed of wave on the string times over 2 by 2 times the length of the vibrating string. So let's try a simple problem. So they have given us what are the first three harmonics in a 2.45 m long pipe that is open at both ends. What are the first three harmonics? One end. When one end of the pipe is closed, assume that the speed of the sound is in air is 345 meters per second. So they have given us the velocity. So let us write our given. So uh, our velocity is equal to 345 meters per second. While our length is 2.45 meter. So what are we going to find? The first three harmonics. So our unknown would be case 1, F1, F2, F3. And on case 2, wherein the end of the pipe is closed, which is also F1, F2, and F3. So they have given us the what are the three harmonic in a 2.45 meter long pipe with an open end at both ends, and the first three harmonics when one end of the pipe is closed. So let's assume that the speed of the sound in the air is 3.45 meters per second. So they have given us the velocity, so which is 345 meter per second, and they also given us the length of 2.45 meters. So now let's start with the F1. So F1 is equal to V over 2L, which is equal to 345 all over 2.45, and the answer is 70.4 hertz. So for F2, we're just going to do the same, which is the formula is 2F1 is equal to 2 times this one, 70.4 is equal to 140.8. And for F3 is 3F multiply 3 multiplied by F1 is equal to 3 multiplied by 70.4, which is equal to 211.2 hertz. That is the answer for our open ends in both sides. And for the closed one, so we will going to find it using our formula. F1 is equal to V L over 4L is equal to 345 multiplied over 4 multiplied by 2.45. So the answer is 35.2. So for our F3, it's going to be 3F1 is equal to 3 times 35.2, which is equal to 100.6 hertz. And for our F5, is equal to 5F1 is equal to 5 times 3, 5.2 is equal to 176 hertz. So now we are done with the wave. You might be wondering why I take too much focus onto the wave. Well, it's because if you take any system, disturb it from equilibrium, from a stable equilibrium, the resultant motion is wave and vibration. So now let's talk about Robert Hooke, born in 1625 to 703. He is a English physicist, mathematician, and English inventor. He coined the term cell, and he looked up dead cells using microscopy and discovered a law for elastic material. He was trying to improve the type of clocks that were used on ships. It is called pendulum clocks, and theorized that a spring would look better on a pitching ship. So Hooke's law states that the force needed to compress or extend a spring is directly proportional to the distance you stretch it. So one type of periodic motion is the motion of a mass attached to a spring. The direction of a force acting on the mass is always opposite direction of the mass displacement from the equilibrium. So let's say there are three positions here. You can see this is from the maximum displacement. It's the equilibrium which the rest, and this is the maximum displacement again. So now we are keeping it in a normal state in the equilibrium, and when you stretch it and apply a certain force, the spring stretched to the spring, it vibrates this body between two positions from extreme position where the spring enlarged. This is the maximum displacement when the x is going right, and this is the and they are in here you can see that they are all away from each other. It's refraction. So if you move the x into negative, and then everything will be compresses, and there will be, and if you let it go, it will start to vibrate until it return to its equilibrium, which is wherein x is equal to 0. So at equilibrium, the spring force and the mass acceleration became 0. The speed reaches a maximum. So at maximum displacement, the spring force and the mass acceleration reach maximum and the speed becomes 0. So the law basically say that if we know that the equilibrium, the spring force and the mass acceleration becomes 0, so the speed reaches its maximum. While at its maximum displacement, the spring force and the mass acceleration reaches the minimum. While the speed became 0 here in the equilibrium, the maximum speed with no displacement and minimum, so there is a 0 acceleration. And when you are at the maximum displacement, the spring and the mass's acceleration are at the maximum, but the speed becomes 0. Notice here that the speed continuously slows down once it reaches its limit, and it becomes the maximum and goes back to its original value again at the equilibrium. So the measurement shows that the spring force and the restoring force is directly proportional to the displacement of the mass. So here we have x as the displacement, and k is equal to spring constant. So Hooke's law is F is equal to negative k, or the negative spring constant multiplied by the displacement. It says here that the spring force or the restoring force is directly proportional. So it is the opposite here in our equation. So that's why the negative here implies, because being negative means is the opposite or proportional. So spring force is equal to spring constant negative. This is the proportional. Spring constant multiplied by the displacement. And the quantity K is a positive constant called the spring constant. So let's take this as an example. So if a mass of 0.55 kilogram attached to a vertical spring stretches the spring to negative 2.0 centimeter from its original equilibrium, what is the spring constant? So here we have the negative 2.0 cm, which is the stretches centimeter, and we are starting at 0, so you have x equal to 0, and also you have the plus x as well in the opposite direction. So the given here is k is equal to 0.55 kilogram, negative x is equal to negative 2 centimeter, and our solution is our formula is f is equal to negative kx. But since we're going to find the k, so we're going to convert it. So it's going to be k is equal to f over negative x. So now let's input our values. So k is equal to 0.55 multiplied by 9.81 all over negative 2.0 centimeter. So we're gonna factor out. So 0.55 times 9.81. 9.81 is going to be positive, and the answer is 269.775. And our final answer would be 270 Newton per meter. So, the motion of a vibrating mass spring system is an example of simple harmonic. This should describe any periodic motion that is the result of a restoring force that is proportional to a displacement. So, force is a proportional to displacement. So if a force is proportional to displacement, then all of these forces that describe this kind of motion can be called a simple harmonic motion. Because simple harmonic motion involves restoring force back and forth motion over the same path. So we have a chart over time. So let's say that this is the x-axis. So we have the negative x-axis and the positive x-axis and the equilibrium. So notice that we are going to start from the equilibrium position, which is at 0. So in such a the so the spring oscillates in such a way that it reaches plus x. Let's say it reaches plus x after a certain amount of time, then back to its equilibrium position and going to the negative position. So that is how oscillation happens. So from the equilibrium, it will oscillate to the plus x-axis, going back to the equilibrium, then going to the negative x-axis, then going back to equilibrium. Then again, until the cycle of ends. So the waveform here is called a sine waveform. So if you consider the motion, the function of x and t to be sine wave, we can call this a simple harmonic motion. So here, one of the example of is a simple pendulum. Now, a pendulum is attached in a rigid surface, and it has a mass m. And if you tilt it to another maximum displacement, so the angle from the equilibrium to the tilt place is, let's call it a angle theta, and that is the maximum displacement. And also, the other side is also called the maximum displacement. So let's create a free body diagram. So we will so this is the mass. It is in the uh, center of the material, the pendulum, which is going downwards, which is Fg, and that Fg is equal to mg. Now you have a force which is the tension, which is this one, tension from the string along the path of the string. Now, if you continue writing down the tension of the string, this angle becomes equal to theta. So, from here to here is the tension of the string, and it became the angle theta from the Fg. Because this is attached again to theta, becomes Fg sine theta. So, from the free body diagram, we can say that this is the force and the this applied force right here, and the restoring force acts in this direction. So we have a Fg sine theta here. So this is F and Fg sine. This is from the laws of mechanics. We can simply say that tension equals Fg cos theta, and this force applied force, and this is the restoring force. This is the applied force, and this is the restoring force, and there is the applied force. So let's consider this. This is the applied force equal to Fg is equal to sine theta, and the restoring force is negative Fg sine theta, because because the restoring force is the opposite of the applied. So the restoring force becomes negative while the applied force is the positive. So MA is equal to FG sine theta. And we all know that FG is also can be write as MG. So MA is equal to MG sine theta. So what we're going now let us consider the idea here. So to remember that the force is directly proportional to the displacement. So how would you consider that the case here? So we have to prove that the force is directly proportional to the displacement. So let us consider m being a really small value. So we know that sine 0 is equal to 0 degrees, while sine theta, we can approximately it near to sine theta, to approximately to theta. So let us consider MA as the force. So force is equal to mg theta. So from this pendulum, so as you can see, this is the arc S, and this would be the length of the pendulum string. So let us consider, let's change this arc into X. So let us consider that the radius, the arc here is X, and over the radius, so it would, the formula will be force is equal to mg multiplied by the arc all over the length. So because we're looking for the restoring force, so we will now get the force is equal to negative mg all over the length multiplied by x. So this is our uh, this two proves that force is proportional to x. And if you will write the Hooke's law is equal to F is equal to negative K X. So still it is negative. So it also proves that it is proportional. Force is proportional to X. In this case, we can also rewrite this as K is equal to negative mg all over L multiplied by x. So what happens here in terms of simple harmonic motion is when the pendulum is or any material is on the equilibrium position, then the acceleration is 0 while the velocity is max, because as you can see, there is no decreasing or increasing of acceleration, it's just resting. While over here is the maximum displacement wherein the acceleration is max but the velocity is 0. So now let's talk about measuring simple harmonic motion. So again, let's talk about amplitude, period, and frequency in simple harmonic motion. So a pendulum's amplitude can be measured by the angle between the pendulum and the equilibrium position and its maximum position. So the angle here is the amplitude. And for the mass spring system, the amplitude is the max amount of the spring stretched or compressed from its equilibrium. So these two, this one and this one. The SI unit is second. The SI unit of period is second. So one period is basically from the equilibrium going back and then coming back to the equilibrium again. So the SI unit of frequency is hertz. Amplitude, period, and frequency in simple harmonic. Period and frequency are inversely related. So F is equal to 1 over T or T multiplied by 1 over F. Thus, anytime you have a value for period or frequency, you can calculate the other value. The period of the simple pendulum depends on the length and on the free fall acceleration. So period is equal to 2 pi square root of mass over spin constant, wherein AG is equal to free fall acceleration and T is equal to 2 pi square root of L over AG, wherein G in AG is equal to 9.81 meter per second squared, and T is equal to 2 pi square root of length over G, and the period does not depend on the amplitude. The equation applies only for system in which the spring obeys Hooke's law. So that's it for our today's chapter. Thank you for listening.